Assalamu alaikum. Today we want to talk about chapter 3, Stoichiometry, calculations with chemical formulas and equations. Stoichiometry is the area of study that examines the quantities of substances consumed and produced in chemical reaction. It is built on an understanding of atomic masses, chemical formulas, and the law of conservation of mass. Remember that atoms are neither created nor destroyed during any chemical reaction or physical process. Look, here we have the reaction of sulfur plus iron to produce Fe(S). The atoms are neither created nor destroyed. And if you add the masses, 32 gram plus 56, these are called reactants, we will get 88 gram products. Chemical equations. Chemical equations are concise representations of chemical reactions. If we look at this equation, the combustion of CH4 by oxygen into CO2 plus water, we see that this is a balanced equation. Here on the left side, here we have 1 carbon atom, 4 hydrogen atoms, and here we have 4 oxygen atoms. On the side of the products, we have 1 carbon atom, here 2 oxygen atom, here 2 oxygen and 4 hydrogen. If you add all of these, you will get this, the same number of atoms on both sides. So reactants appear on the left side of the equation, as you can see, and then products appear on the right side of the equation. Now the states of the reactants and products are also written in parentheses to the right of each compound. Here, gas, 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 gas. If it is solid, then it is small s. If it is liquid, small l, and so on. After you balance an equation, you get numbers in front of either a reactant or a product. This number is called a coefficient. Coefficients are inserted to balance the equation. So here 2 is a coefficient in front of oxygen, and 2 here in front of water. This is only to balance equation. As you can see here, we have 4 hydrogen atoms, and here we have 4 hydrogen atoms, 1 carbon, 1 carbon, 4 oxygen, here we have 2 plus 2, and here we have 4. Now, subscripts and coefficients give different information. Here we have the chemical symbol water, meaning 1 molecule of water, composition 2 hydrogen atoms and 1 oxygen atom. Now, subscript tells the number of atoms of each element in a molecule, as you can see here. Now, coefficients, however, tell the number of molecules. Here we have 2 molecules of water. So the composition is 4 hydrogen atoms and 2 oxygen atoms, as you can see here. Now we come to the so-called formula weight. Now, a formula weight is the sum of the atomic weights for the atoms in a chemical formula. So the formula weight of calcium chloride, for example, CaCl2, would be calcium. We have 1 atom. Here we have the atomic mass, 40.1 AMU. For Cl, it is 35.5 AMU, and then we add them all together. Then we call this the formula weight for CaCl2. Formula weights are generally reported for ionic compounds, usually. Molecular weight is the sum of the atomic weights of the atoms in a molecule. So for the molecule called ethane, C2H6, the molecular weight would be, we have 2 carbons times 12 AMU, and 6 hydrogens times 1, and the total is 30. So here again, the formula weight of a substance is the sum of the atomic weights of each atom in its chemical formula. Example, H.2SO4, 2 hydrogen atoms times 1 AMU, 32 for sulfur, 4 times 16 for oxygen, the total is 98. Now for molecular compounds, the formula weight is also called the molecular weight. For ionic compounds, however, no separated molecules, so it is called specifically the formula weight. Now for elements, in case of isolated atoms, is called atomic weight. So here the formula weight of NaCl is atomic weight of sodium, 23, plus 35.5 for chlorine, and it is 58.5 AMU. Here we have sample exercise. Calculate the formula weight of sucrose. Molecular weight here, or formula weight of sucrose, is the sum of all atomic weights. For calcium nitrate, the same. And here you can practice this exercise by yourself. Now we have something called percent composition. Is the percentage by mass contributed by each element in substance. Percent composition generally can be calculated by using this law: percentage composition, mass of part over mass of whole times 100. Percent element equal number of atoms of that element times the atomic weight of that element divided by the formula weight of the compound times 100. Now example for C2H6, molecular weight is 30 AMU. Percentage of carbon, we have 2 atoms times 12 divided by 30 times 100, so it is 80%. Percentage of hydrogen, we have 6 atoms times 1 divided by 30 times 100, and we have 20%. So this is the percent composition of carbon 80 and of hydrogen 20. Notice that the sum of them is equal 100. And here we have a sample exercise. Calculate the percent of carbon, hydrogen, and oxygen by mass of this in the same way. 12 carbon atoms times 12 atomic weight divided by, this is the molecular weight of this compound, times 100. This is the percentage of carbon, this is the percentage of hydrogen, and this is the percentage of oxygen. Again, if you add them, the total is 100. Also, you can practice in this exercise, calculate the percentage of nitrogen by mass in calcium nitrate, and you can check your answer. Avogadro's number and the mole. Now the mole is just a few things. In daily life, 1 dozen equal 12 things, 1 pair equal 2 things, 1 gross equal 144 things. In chemistry, the unit for dealing with the number of atoms, ions, or molecules, any particles, the mole abbreviated mole like this. Na is abbreviation for Avogadro's number. It's equal 6.02 times 10 to the 23 per mole, representative particles. So, for example, if we have 1 mole of carbon 12 atoms, it contains Avogadro's number of carbon 12 atoms. If we have 1 mole of water molecules, then we have Avogadro's number of water molecules. If we have 1 mole of nitrate ions, then it contains Avogadro's number of nitrate ions, and so on. To understand this, let's look at this sample exercise. arrange the following samples in order of increasing numbers of carbon atoms. Here we have 12 gram of carbon 12, 1 mole of C2H2, 9 times 10 to the 23 molecules of CO2. We want to arrange them in order of increasing numbers. Now, 12 gram of carbon 12 equal 1 mole of carbon atoms, and this 1 mole contains Avogadro's number of carbon atoms. Now, 1 mole of C2H2 contains twice the number of carbon atoms. Contain this number of C2H2 molecules, and each molecule contains 2 carbons, so 2 times Avogadro's number of atoms. 9 times 10 to the 23 molecules of CO2. Since we have only 1 carbon atom, it contains the same number of carbon atoms. So you can arrange these now in the following way. The 12 carbon of carbon 12, 1 mole of carbon, is smaller or less than 9 times 10 to the 23 CO2 molecules, which represent 1.5 mole of carbon, and at the same time this is less than 1 mole C2H2, which is equivalent to 2 mole of carbon. Important notes. 1 molecule of H2SO4 contains 2 atoms of hydrogen, 1 atom of sulfur, 4 atoms of oxygen. Now 1 mole of H2SO4 contains Avogadro's number of molecules of H2SO4. 1 mole of H2SO4 contains 2 moles of hydrogen, which means twice Avogadro's number of atoms of hydrogen. 1 mole of sulfur, Avogadro's number of atoms of sulfur. 4 moles of oxygen, 4 times Avogadro's number of atoms of oxygen. Remember this. Now again, here we have sample exercise. Calculate the number of hydrogen atoms in 0.350 mole of C6H12O6. This is glucose. Now this is the solution. We want to convert moles of glucose into molecules of glucose into atoms of hydrogen, and this is like one step. You can use this one step for all of them. A number of hydrogen atoms. First you convert the moles into molecules. You multiply this by Avogadro's number. You cancel this. Then each molecule contains 12 hydrogen atoms. You multiply by 12. Here molecules with molecules cancel out, and here you get your final answer, which is equal to 2.53 times 10 to the 24 hydrogen atoms. Now we come to the so-called molar mass. By definition, a molar mass is the mass of 1 mole of a substance. The unit is gram per mole. The molar mass of an element is the mass number for the element that we find in the periodic table. For example, sodium 23. The formula weight in AMUs will be the same number as the molar mass in gram per mole. So, AMU will be equivalent to gram per mole. Now, this figure compares the mass of 1 molecule and 1 mole of water. You see here, this is 1 mole of water, which weighs 18 grams. This is lab size sample. It contains Avogadro's number of molecules, like this, as you can see. So it is like this always. 1 mole of anything contains Avogadro's number of that thing. So 1 mole of carbon 12 has a mass of 12 grams. Now, if we look here at this mole relationship at this table. If we take nitrogen, atomic nitrogen, formula weight 14, molar mass again 14 gram per mole. It contains Avogadro's number of nitrogen atoms. Molecular nitrogen N2, formula weight 28, as well as the molar mass. It contains Avogadro's number of N2 molecules, but it contains twice the amount. It contains twice the amount of Avogadro's number of nitrogen atoms. Now silver, formula weight 107.9, as well as the molar mass, contains Avogadro's number of Ag atoms. Silver ions, you see the same. Barium chloride, the formula weight is 208.2, molar mass the same. So look what it contains. It contains Avogadro's number of BaCl2 units. Why? Because it is an ionic compound. Avogadro's number of barium ions and 2 times Avogadro's number of Cl- ions. So 1 mole of atoms, ions, or molecules contains Avogadro's number of those particles. 1 mole of molecules or formula units contains Avogadro's number times the number of atoms or ions of each element in the compound. As we saw here, 2 times Avogadro's number, 2 times Avogadro's number, and so on. Now here we look at this sample exercise. What is the mass in grams of 1 mole of glucose? Again, the molecular weight of glucose is found by adding H. It is the sum of atomic weights of elements or atoms. We have 6 carbon atoms times 12 plus 12 hydrogens times 1 plus 6 oxygen times 16. The total is 180 AMU, and so 1 mole of glucose, which weighs 180 grams, and the molar mass is 180 grams per mole. So from now on, don't worry about AMU, just know that the molecular weight, the unit of molecular weight is gram per mole instead of using AMU. And again here you could practice this exercise, calculate the molar mass of calcium nitrate, and then you can check your answer. Thank you. End of part 1.